Ever feel like we barely scratched the surface of the universe? Like there's a whole other level of reality just out of reach.
Well, today we are diving into a project that could blow that whole other level wide open.
We're talking about the Compact Linear Collider, or CLIC.
And we're going deep into this 2018 report that lays out the plan to make CLIC a reality.
It's fascinating stuff. Okay, so CLIC, massive machine, we're talking miles long,
It is.
smashing electrons and positrons at ridiculous speeds
Add on.
to unlock the tiniest secrets of the universe. It's kind of mind-blowing when you think about it.
It's all about energy. The higher the energy of those collisions, the smaller the details we can see.
So it's like using a more powerful microscope to zoom in on the universe's tiniest particles.
Exactly. Think about the standard model of particle physics. It explains a lot, but it leaves a lot of questions unanswered.
It's like we've put together the edges of the puzzle, but that middle part is still a mystery.
Right. And that's where CLIC comes in. Dark matter, antimatter, how the Higgs boson really works. CLIC was designed to tackle these big questions.
And to do that, they were talking about building CLIC in stages, right?
Yeah, they'd start by smashing particles at 380 GeV.
Gigaelectron volts.
Gigaelectron volts, a measure of energy.
Okay, so that's got to be a lot of energy, but like, what does that actually look like?
So for comparison, the LHC, that's the Large Hadron Collider, discovered the Higgs boson at around 125 GeV.
Okay.
CLIC would blow that out of the water, potentially uncovering particles we haven't even dreamed of.
See, that's what gets me fired up. The possibility of finding something totally new, something that changes our entire understanding of how everything works. And to get to those energy levels, the report talks about two possible approaches.
One uses klystrons. They're kind of like really, really powerful microwave ovens that accelerate the particles.
So like a super-powered microwave that instead of heating up your leftovers, accelerates particles to nearly the speed of light?
Basically,
That's wild.
it is. But the second approach is even more wild. They called it the two-beam acceleration method.
This is where it gets really cool. It's like they said, hey, instead of plugging this massive collider directly into the power grid, what if we use a second supercharged beam to power the whole thing?
You got it. Imagine a giant linear accelerator acting like a power cable feeding energy to the main beam.
It sounds like something in a Star Trek. Did they actually think this could work?
They were doing experiments. Back in 2018, they were testing this at facilities like CTF3, ATF2, Facet, and Fermi, just to name a few.
And those tests were going well.
This report is packed with details about what they learned.
It's one thing to even consider this two-beam acceleration idea, but then on top of that, they were aiming for nanometer precision in controlling these beams. Nanometer precision, it's mind-boggling.
They had to. To really understand the data from the collisions, they needed that level of control. It's pretty incredible stuff.
Okay, so you've got these particles, they're smashing together at these insane speeds.
The crazy energies.
But then what? How do you actually see what happens?
Well, that's where CLICD comes in. That's the detector that was specifically designed for this collider.
So what are we talking here? A super high-speed camera trying to catch a glimpse of these tiny particles.
Basically, but even faster. CLICDO would have to handle a truly ridiculous amount of data, way more than anything we've ever seen before.
Yeah, I bet. Sifting through all that to find the actual important events, it must be like finding a needle in a haystack.
It's a huge challenge, and the detector design has to account for all that. It's not just two particles colliding, it's more like two swarms of particles colliding all at once.
Okay, yeah, that definitely complicates things. So how do they even start to make sense of all that data?
Well, this is where the details really matter. This report goes into things like the silicon pixel vertex detector, which I'll admit can sound a bit intimidating at first.
Definitely intimidating, but if I'm picturing this right, it's kind of like a really, really high-resolution camera placed right at the heart of the collision.
Exactly. That's a great way to think about it.
And that's capturing the paths of these brand new particles that are created in the collision.
You got it. But it's not just about seeing where they go, it's also about figuring out how much energy they have. That's where the calorimeters come in. They measure the energy deposited by different particles.
And I remember reading in the report about different types of calorimeters. Electromagnetic calorimeters for lighter particles, hadronic calorimeters for heavier particles.
Right, and there's this concept of granularity that they talk about, which refers to basically how detailed these calorimeters are. The more granular, the more precise the energy measurements can be.
So it's like the more pixels you have in a digital camera, the sharper the image.
Exactly. That's a great analogy. And with particle physics, it's all about getting the clearest picture possible.
Yeah.
And just to give you an idea of the scale, they were actually developing completely new software just to analyze the data from CLICD.
Wow. So much work just to analyze the data. I mean, this thing is powerful on a whole other level. So we've got this insanely powerful collider, this incredibly detailed detector. What are we actually looking for here? What were they hoping to find with CLIC?
One of the most exciting possibilities was evidence for supersymmetry.
Supersymmetry, what is that? I feel like I've heard that word before, but...
It's a really cool idea. Basically, it suggests that every particle we know about has a partner particle, a superpartner, with a different spin.
So it's like every particle has a twin, but they're not exactly alike. Kind of like the evil twin in a comic book.
Yeah, a good way to think about it. It's like the standard model of particle physics is only half the story. Supersymmetry would be the other half.
Okay, so that's cool and all, but what's the big deal? Why would these superpartners matter?
Well, for one, they could help explain some pretty big mysteries, like dark matter.
Ooh, dark matter, the universe's biggest mystery. I'm listening.
Right. So we know that dark matter is out there. We can observe its gravitational effects, but we have no idea what it is. Well, some of these hypothetical superpartners actually fit the profile of dark matter perfectly.
They could be the missing pieces of the puzzle.
Exactly. And with CLIC, we could finally have the tools to actually find them.
That's wild. Okay, but I do remember something about the hierarchy problem.
The hierarchy problem, yeah.
It sounds kind of ominous. What's that all about?
It's a big question in physics. Basically, why is gravity so much weaker than all the other fundamental forces?
Yeah, it's kind of weird when you think about it.
Yeah, it's like comparing the weight of an elephant to the weight of a feather. They just shouldn't be that different. The standard model doesn't really explain it, but supersymmetry with those superpartners might actually be able to.
So supersymmetry could solve multiple mysteries at once.
Potentially, yes. It's kind of like a domino effect. Each discovery could lead to another and another until we have a much clearer picture of how the universe really works.
And this report, it mentions that CLIC could even help us understand the stability of the universe.
It all comes down to the Higgs boson, that particle we talked about earlier, and something called the Higgs potential.
The Higgs potential, that sounds intense. What is that?
Think of it like this. Imagine you have a ball at the top of a hill.
Okay.
Now, if the ball is in a stable position, it'll just stay there. But if it's in an unstable position, even the slightest nudge will send it rolling down.
Right. Makes sense.
The Higgs potential is kind of like that hill, and the universe is like the ball. By studying the Higgs boson, CLIC could tell us if the universe is in a stable or unstable state.
So basically, whether or not the universe is going to stick around for a while. No pressure, CLIC.
Right? This is fundamental stuff we were talking about.
No kidding. It's incredible to think that this was all being planned back in 2018. Makes you wonder what physicists are working on right now.
Right. What new discoveries are just around the corner? What amazing machines are they dreaming up?
It's truly mind-blowing. Well, that's it for our deep dive on the Compact Linear Collider. Huge thanks to our expert for breaking down this fascinating project.
It's been my pleasure.
And to all you listeners, thanks for joining us. Until next time, keep exploring the universe, keep asking those big questions, and we'll see you in the next deep dive.